So in case this is the 20th webinar that you've signed up for this week, the one you're in right now is selecting the right tools for your application. Part 2, understanding press fit techniques. So during part 1, we discussed servo press basics, some of the application mechanics that we deal with on a regular basis. This second part is going to cover some of those applications more in depth, as well as some unique applications we've been a part of in the past. So my name is Ed Stockline. I'm a territory manager here at Promess for the West Coast. I have a background as sales and application engineering here at Promess alongside my co-presenter today, Eric Britton. Eric, tell people who you are.
Thanks, Ed. Hello, my name is Eric Britton, and I have been an application engineer for Promess for over 16 years now. In my time with Promess, I've traveled all over the world setting up systems and programming some of the most difficult and fun applications.
Eric's one of my go-to guys whenever I run into a engineering problem that I can't solve. He's one of the first people that I go and talk to hash out ideas. So just to give you guys an idea, in today's presentation, I'm going to give you a little summary of who Promess is and what we do. And then we'll start the press techniques portion of that, which Eric will be presenting. So just some housekeeping items. Use the sidebar on the right of your screen for questions during the presentation. You can input those questions during the presentation and we will get to them at the end, where we'll have a little Q&A period. We'll try and keep this wrapped up for you guys around half an hour, but if the Q&A period lasts a little bit longer than that, we'll just keep answering questions basically until we run out. About Promess. For those of you that don't know, I know a lot of you are already current customers of ours, just looking to learn a little bit more about what we do. Promess is a technology company located near Detroit, Michigan, Brighton, Michigan specifically, if you're familiar with the area. And I guess if I could describe our company in one simple sentence, it would probably be that Promess is a company that's passionate about giving machines feeling. So in short, giving machines a sense of touch allows us to inspect and verify parts as we make them. So how can that benefit you? Well, we're the experts at integrating sensors into actuators that build many of the products that you guys use every day, from vehicles and components, kitchen and home appliances, hand and power tools, even things like boats and golf clubs. Manufacturers rely on us to catch bad or out of specification parts before they ever leave the factory, which avoids some quality and warranty issues. So just as a side note, think about a recent time where something you bought specifically didn't perform the way that you imagined, or even worse, broke when you needed it the most. Because of that, you'll likely probably never buy that product again. So Promess is kind of in the business of making sure that doesn't happen with any of our clients' products. And finally, our systems provide data that helps our customers make educated decisions about their parts and processes. Also, how to improve those processes over the life of the product. So everyone kind of talks about Industry 4.0 and gathering as much data as possible. But in reality, if you're only collecting data and not actually doing anything with it, if you never look at it again, how does that really benefit you? So if you can use that data that you're collecting to find upstream manufacturing problems, or use it to make more consistent downstream products, how much more is that process really worth to your company? So what are the tools that we use? So this is a short list of our main products. So we are the world leader in servo press technology. We provide standard workstations where a custom solution doesn't always make sense. Pro systems allow for us to use the same features and monitoring as our presses, but on applications that require torsion instead of linear travel. And our remap, which combines the press and torque technology into a single actuator for applications that need both axes of motion. So I do have a little educational disclaimer for you guys real quick. So during this webinar, we're trying to keep the content within it as educational as possible when discussing some of these techniques. So while education is our intent, there are some software and hardware capabilities to keep in mind that are unique to the systems that Promess provides. So in some ways, we may be the only company that we know of that's able to perform some of these techniques. So if you are looking at selecting a servo press or doing some press fit applications, make sure to check with your individual press supplier on whether or not those capabilities are available for your application. So now we get into the meat and potatoes of the presentation. So there are many ways to assemble a part or sub-assembly. Our favorite, as you can probably tell, is the press fit. So using sensors to monitor how well a part goes together is not new, but we do believe it is a great way to join a lot of assemblies, especially for critical applications that involve safety or a strict functional purpose. Eric is going to cover some of the most effective ways to assemble parts using a servo press and explain some of the nuances of why we implement certain techniques for certain applications. With that, I will turn the presentation over to Eric. Go ahead, Mr. Britton.
Thanks, Ed. So back in the old days, parts were assembled using hammers, manual presses, or hydraulic presses, which is good for their time, but as the need for better accuracy and precision increased, so did the need for a better solution. Using servo technology, you can control that assembly using a more precise technique. There are three basic methods that can be used to assemble the part. These methods are pressing to a position, pressing to a desired force, or pressing to a part's functionality. There are many ways to press to a position when assembling a part. Typically, the application drives the method as to which way you want to press to that position. The different methods include pressing based on the feedback from the servo motor, based on feedback from an external position sensor, pressing based on a touch point, or pressing based on information from a separate process. So when pressing to a position based on feedback from a servo motor, you basically tell the servo motor where you want to go, and it extends the press to that position. This method doesn't take into account any stack up in the part, it just presses until the programmed position was met. It also doesn't consider any deflection in the tooling, just simply moves to that position. An example would be pressing a dowel pin into a housing. You don't necessarily care about the final position, you just want to make sure the part reaches position within the housing. Pressing based off feedback from an external position sensor allows you to press to a critical dimension within the part using that external sensor. This method takes away machine deflection. It also gives you better feedback about the part relative to the part housing or critical dimension within that part. For example, using the dowel pin from previous method, when pressing a pin into a housing, if the pin has to be set to an exact position, but you have part height variation, you can't rely just on pressing to a position out in space. You would need to bring an external position sensor into the equation to be able to press to that critical dimension repeatedly. while taking deflection and part variation out of the equation. Using integrated force sensors, the press can move to a small force to be able to locate the part and find that touch point. And then from there, you can move a relative distance. This allows you to press to a position based on where you contact the part, instead of just pressing to a position out in space. Pressing to a position based on information from a separate process would typically take information from an external source such as a PLC and transfer the information to the controller to tell the press where to go. To elaborate on this a little more, I'd like to take an example of adding shims to a housing. So you'd have your PLC, the Promess controller, and the Promess press. And in my example here, I want to press to a desired position of 10 millimeters. So the PLC would take information from an external source, such as an external gauge or something, and send that information over to the Promess controller. So in this example, a shim of 0.2 millimeters would be sent to the Promess controller, and then to get my desired position of 10 millimeters, I would subtract the 10 minus 0.2 millimeters to give a final position of 9.8 millimeters. So we would send that position to the press. The press would move until it reached that position, send the feedback to the Promess controller, and then we can pass the information saying that we've reached the 10 millimeters final position back to the PLC. We can also use this method if you had an HMI and you didn't want the operator to get in to make any adjustments to the actual program, but if you were constantly changing forces or positions for your process, you can program it on the HMI where it just sends that value over to the controller. Many applications require a certain force to be met to ensure that the part was properly seated in the housing. To do this requires real-time feedback and control. The system must take into account force sensors in real time and control the process of the press until the desired force is met. A few methods of this is pressing to a hard stop or pressing to a relative force. When pressing to a hard stop, this method allows the system to continue pressing until it achieves the desired force. Typically, the force that you press to is more than what it actually takes to press the part, but you want to ensure that you've fully seated the part. The two ways of pressing to a hard stop are, well, the first way is pressing until the part bottoms out internally, causing the force to increase exponentially as the part hits the internal stop of the housing. For instance, if you have a bearing and you're pressing it into a housing, you want to make sure the bearing is fully seated in the housing, so you would move to a force to know that you've hit the shoulder. The second way is to use the tooling to generate the hard stop against the housing. With this method, the tooling is designed so that it will hit the housing at the point where it sets the part to the correct depth. For example, if you're pressing a ball into a housing to block a hole that was drilled, you would want to set the depth of the ball using the tooling to hit the shoulder. This way, you make sure that the depth of the ball is below the surface, but it's not too deep to block any internal workings of the part. When pressing to a relative force, the system must take into account the force value at a certain position and calculate how much more to press the part. As shown on the graph, the force is captured a few millimeters before the shoulder. At this point, additional force can be added to the force that was captured to set the final force so that you're not pressing the part with more force than what is needed. Advanced pressing techniques utilize both force and position when making decisions on where to stop. A few of the advanced techniques are pressing to a position based on force compensation and pressing to a rate of change. Pressing to a position based on force compensation allows the user to program the position that the press must travel to, but it also takes into account the force. One of the main reasons for doing this is because of deflection in the system. The higher the force you put on the system, the more deflection it sees. An example of this would be installing valve seat and guides into an engine block. With the valve seat, you're pressing to a hard stop, but with the guide, there isn't a hard stop. You're pressing to a position in space. But because of tolerances required, and with deflection in the machine, and because the guide has a lot of surface area to cover, any change in the bore or any surface area finish that's not identical, it'll cause a fluctuation in the final force up to 6,000 pounds or more. And the higher the force, the greater the machine deflection. So what you can do is measure that force as you're installing the part and put a compensation factor in on the fly to compensate for any of the machine deflection. Some applications require pressing to the slope of the curve until it meets a certain criteria. One of the reasons for doing this is to know the exact moment that the part has been fully seated so you don't put unnecessary force on the part. Pressing to a rate of change is typically for very sensitive applications where you have to find the knee of the curve and stop immediately as to not damage the part. Calculating rate of change, you're calculating the change in force divided by the change in position. With the Promess system, we have a math engine built into the software to easily do these calculations and press based on the calculation reaching the program value. For example, expansion plugs are used to plug a tapered hole that was drilled in the part. If you press these plugs to a position due to part tolerances or station deflection, you may not press the plug far enough. And if you use a force to press the plug, you may end up pressing the plug too deep into the part. So by using rate of change, you know the exact moment when the plug has been fully seated into the housing and you can stop the press at this point. Pressing to a function is more of a specialized move because you are not just pressing to a force or a position, but you're pressing to the component to make it function properly. By not pressing the part enough, the part would be loose and could potentially fall apart during operation. Pressing the part too much could cause the part to seize up, becoming inoperable. So what you would want to do is test the functionality of the part while you are assembling it. An example of pressing to a function is like pressing together hand tools such as pliers. A cheap pair of pliers may just be assembled to a position or a force, but they're cheap for a reason. The feel from one pair to another may not be the same, and they may not work properly, or they may easily fall apart. Higher end pliers have a nice feel to them because they're typically assembled using servo technology and assembled to their function. You wouldn't want to pay a higher end cost and not have them function properly every time. So the part has to be assembled and functionally tested as you're making the part. But pliers are just one example of a hinged part that can be functionally tested as it's being assembled. We've worked with many other applications, including tilt and telescope steering columns, car door hinges, linkages, and more. We have even done things like pressure relief valves and fluid flow valves, adjusting them during their assembly. Really, anything you can measure its function as you're putting it together, you can potentially use that measurement as a function and feedback for the assembly. Also, the nice thing about pressing to a function is that when you have variation in your parts, you're going to have variation in your final assembly. But if you're pressing the part to its functionality, it compensates for the variation in the pieces that make up the part. And with that, I will give control back to Ed.
Thanks, Eric. So today, Eric covered a lot on the most popular aspects of press fit techniques. There isn't really enough time to cover every aspect of our applications in a webinar format like this. But on this page, in particular, you can see more applications that we've been involved with in the past. So if you do think that you have a specialized applications, if you think you have a specialized application, chances are we've probably seen something similar in the past. So now we do have some time for questions. The first question that I have for you, Eric, is from a guy named Jeff. So how fast can you actually press?
So our standard pressing, we can move the press at 200 millimeters per second, but because this is a servo-controlled ball screw press, you don't want to slam into the part at 200 millimeters per second. So typically you would wrap it down to the part. Typical applications, and it really depends on how critical that final position is. You can press between 5 to 10 millimeters per second as you're pressing the part. But if you're pressing to a hard stop and you have to make sure that you're seating and not overshooting the value you're trying to reach, you would want to keep at a slower speed, so you're not just slamming the part together.
Okay. And Marcus asks, can you drive to a force and hold the force with a brake?
Well, yeah, you can drive to the force, and if you have a safety brake, you can hold it, but you can also hold it with the servo motor. With the way we size our systems, we size them in the continuous range of the motor. So when you press down and hold the force, you can sit there holding the force with a servo motor for an undefined period of time.
Okay. John asks, is the internal calculator that calculates the rate of change standard on all models, or does it add to the cost to do a design? And does this calculation slow down the speed at which a press can operate?
The math engine is a standard component inside our software. So even if you're not using it, it is there. And the other part of the question, Ed, that was
does this calculation slow down the speed at which a press can operate?
That all depends on how fast. If you're using it to press to a shoulder, and you have reaction time for the system to stop. So by pressing it slower, you're going to find the knee and stop quickly. The faster you press, the software is calculating on a 1 kilohertz basis. So it's every millisecond basically. It's taking a sample and doing the calculation. So but the press reaction time is really where it comes in. If you're pressing slow, the press will react quicker and stop. But if you're pressing faster, you may overshoot the knee a little bit. So it's just a matter of how much overshoot you can take inside your process.
Okay. Can external load cells be used to press parts with assembly force ranges lower than the capacity of the press?
Yeah, and we do this quite often where some applications require a large force, but they also have components that are pressed together using a very small force. So typically we'll have 1 or 2 external force transducers wired into the system as well, and we can control those processes to the external force transducer so that you can get a very small range within when you're pressing those smaller parts, but also have a lot of overhead if you're pressing a heavier component as well.
Someone asked, what is the typical scan time to update force readings being sent to a PLC over Ethernet IP?
That is a good question, and the scan time, I believe, usually we're sending samples back to the PLC every 8 milliseconds, but I would have to check with that as, but I'm pretty sure it's every 8 milliseconds.
Okay. Someone asked, can a press be set to hold a force for a period of time and adjust in both directions as the part expands or contracts?
Yeah, we do this quite often with some bearings, as if you had to hold a bearing as you heat it up or cool it down. We've done applications where we can apply a force and hold that force continuously while the press moves up and down, following whichever path the part is taking. If it's expanding, then we'll have to retract the press, but we can still maintain that force capability on the press. We can also do like we've done applications with like injection molding and stuff where as you're pushing on the part or the plastic that's melted, you have to maintain a constant force so that you're not pressing out too much of the material or too less, and sometimes there's air bubbles within the injection molded plastic, so you want to make sure that you're holding that constant force and adjusting on the fly.
How accurately does the move to force step achieve its target?
That all depends on the speed that you're traveling. If you need to hit that target precisely, you're going to move at a slower speed. But with our software, the way it works is you give it a force that you want to move to, and as the force starts to ramp up, the speed of our process starts to slow down, so that we're seating that part at the force that we're told. But if you're pressing at 10 millimeters a second, 20 millimeters a second, you may have a little bit of overshoot in there, just because, and if you're hitting a hard stop, especially, that's when you'll see the force spike up above what you're actually targeting. But we do slow down as we're pressing in, so that makes it seat that part at the force that we're trying to achieve without too much overshoot.
Great. I think that's all the questions that we have. We are coming to 11:30 here, so thank you everyone for joining us during this webinar. We do have another webinar coming up, actually at the request of one of our customers. So we're going to be covering the remap, which is the rotational and linear actuator that we offer, and Torque Pro Basics. So this is going to cover some of our torque applications and how we use these actuators in a few of those different types of applications. So right now that one's scheduled for May 14th, and you should be seeing invites for that shortly. As always, if you do have any questions about our products or services, any application questions that you have about assembling your product or testing your product, we are available. The main email is promess@promissinc.com. You can visit our website at promissinc.com, or you can call one of our press or torque experts here at the office at 810-229-9334. You can also check our social media, YouTube, Twitter, LinkedIn, Facebook. We're on all of them, and we're putting out constant updates and constant content for you guys to educate yourselves on how to improve your processes. Just one thing to mention, after this webinar, you'll receive a survey. It gives you a chance to tell us how we did and suggest future topics that are important to you. So if you have any ideas of what you'd like to learn about Promess or any of the products or processes that we are familiar with, certainly reach out to us and let us know what you'd be interested in learning about. We're trying to take advantage of, everybody being at home and learning a little bit more about products and processes, and I'm sure you guys are all catching as many webinars as possible, but let us know the content that is important to you, and we'll see if we can incorporate that into future episodes. So I do want to thank you guys all again. If you do have any questions, please reach out to us via any of those contact methods. And thanks for taking the time out of your busy day to join us. We do hope to see you at the next Promess webinar. Thanks, everyone.
Thanks, guys.